Hello everyone, my name is Carlo, and in this video I will present the solution report for the steady state 2 of my two-dimensional heat conduction activity. The main objective of this work is to compare the numerical solution program by myself against a simulation program using commercial software. Okay, first of all, the problem consists of determining the temperature distribution on a square plate with a side length of 1 meter. The boundary conditions are the Dirichlet type. We have a constant 200 degrees Celsius in the top and right boundaries, and also we have 100 degrees Celsius in the bottom and the left boundaries. Physically, since there is no heat generation and we are in a steady state, this is governed by partial differential equation of Laplace. Okay, so here is my MATLAB code. Here, as you can see, the first part, I developed my own code using element, the finite element method. I define a structure mesh 50 by 50 knots, but giving us a total of 2,500 calculation points. The logic of the algorithm is interactive. As you can see in the section code, we can see here at the loop. Right, okay. The temperature of each internal node is calculated as arithmetic average of its four immediate neighbors, top, bottom, left, and right. The program repeats these calculations until the difference between the iteration and the next is less than 1 times 2 to the 10 power minus 4, ensuring convergence. So here it is, as is, I have already run it. Here is the graphic. Okay. Upon executing the code, we obtain this contour map. We can clearly observe the temperature gradient following from the cold zone in the bottom left corner towards the hot zone in the top right corner. Okay, here we are now going to present our console. Okay, to validate these results, I replicate the problem. As I said, here in console, the most critical step is here the mesh configuration. I did not use the default triangular mesh. Instead, I configured my structure mapped mesh with exactly 50 per 50 side divisions. This is fundamental to be able to compare apples to apples, in this case, with numerical code. Now, I use aluminum. Here it is as the base material and apply the same temperatures to the boundaries. After running the simulation to convergence, I obtained the static temperature contours. Here it is also. Finally, here is a direct comparison on the left right side of my code. Okay, so you can see here is the same as equal. Left bottom corner, here is the blue, and top bottom right is the red. As you can observe, the match is practically exactly. The shape of the isotherms, the color, and the spatial distribution are identical for them too. For example, if we look at the 150-degree isotherm here in MATLAB, it crosses the exact same geometric coordinates in both solutions. In conclusion, this exercise demonstrates that the finite difference method, when used with sufficiently dense mesh like 50 by 50, one is an extremely precise and robust tool capable of delivering industrial level resolutions for the regular geometries. Thank you very much for your attention.